So far, we have looked at molecules with one central atom surrounded by terminal atoms. While it doesn't make sense to talk about the shape or invoke hybridization at terminal atoms, there are larger molecules that have more than one central atom, that is, more than one non-terminal atom. What we'll find is that we can describe the shape and hybridization at any atom in a molecule based on what we have discovered with our prototype molecules. It's simply a matter of seeing how many electron groups surround an atom. With 2 electron groups, we have a 180-degree bond angle, and the central atom uses sp hybridization. With 3 electron groups, the bond angle is 120 degrees, and the atom uses sp2 hybridization. With 4 electron groups, the bond angles are 109 degrees, and the central atom uses sp3 hybridization. Take note that when molecules have a lot of atoms, lone pairs are often not shown. You will need to add them to the structure to get to the total number of electron groups. Unless otherwise indicated, we're assuming that all atoms are following the octet rule, so that will show you how many lone pairs need to be added. In this example, we'll determine the bond angles, shapes, and hybridization at 3 different atoms in acetic acid. In each case, we'll start by counting the number of electron groups. First, for the carbon on the left, we see 4 single bonds. This would be 4 electron groups. 4 groups have a 109-degree bond angle. Since all 4 groups go to atoms, the shape at this carbon would be tetrahedral. An atom with 4 groups would have sp3 hybridization. This is much like our prototype molecule CH4, except one of the hydrogens has been replaced by a carbon. For the carbon in the middle, we see 2 single bonds and a double bond. Even though this is an octet of electrons, they come in 3 groups, much like our prototype SO3. The bond angle for 3 groups is 120 degrees. Since all 3 groups go to atoms, the shape at this carbon would be trigonal planar. The hybridization at this carbon would be sp2. For the oxygen on the right, we see 2 single bonds and 2 lone pairs, for a total of 4 electron groups, similar to our prototype H2O. 4 electron groups give 109-degree bond angles. However, the oxygen is only flanked by 2 atoms. When you have a central atom with only 2 terminal atoms, the only choices on shape are linear or bent. Since the bond angle is not 180 degrees, the shape would be bent. The hybridization is sp3. We don't ask about the shapes at the hydrogen atoms or the oxygen atom at the top, since all of these are terminal atoms. When looking at Lewis structures of larger molecules like this, you should always check for octets. Often the lone pairs are not shown in the Lewis structure of larger molecules, simply to avoid clutter in the diagrams. All of our molecules in this course will follow the octet rule unless otherwise specified. So if we were presented with this structure without the lone pairs on the right-hand oxygen atom, we should be sophisticated enough now to know 2 lone pairs would need to be added to complete the octet. So be sure to check for octets around the atoms when you are determining bond angles, shape, or hybridization.